Hi, welcome to hypothesis testing of a mean. Oh, what does that mean about means? I don't know. Let's try and find the meaning of that. Lots of means around here, mate. Oh, and lots of drink here. What a healthy drink this is. This is milk. Okay, and I thought I'd bring some along because you've had all those protein bars in the last presentation. Now you're thirsty. Have some milk, mate. Well, maybe not. What I'm really about here is saying when people make stuff up here, they say, well, we have a mean number of grams of protein, maybe 39 grams per litre, some claim like that. How can we check that? That's our hypothesis. Somebody said, I reckon we have a mean in all our cartons of milk of 39 grams a litre. Can we check that out? When can we check that hypothesis? We're going to start with calling that a statement, a proposal. Can we check it out? Now, I guess you already know that due to random errors and stuff, random variation, it's not going to be possible to absolutely guarantee something. We're going to get distributions of weights and volumes around a central value due to random variation, and that's our normal distribution. That worries some people, not being able to zero right in on that population value. Okay, there's something worrying over here as well. I think there's a couple of cans up here. It's called Purple Cow. Wow, I haven't had the courage to actually open these cartons yet, because if they came from a purple cow, would the milk be purple? Oh, yuck. Oh, let's go and do some work. I think there's enough of that. Okay, so coming down here we have what we're going to do. We're going to say the population is normally distributed. Okay, and for this sort of product here, there are going to be random factors governing the amount of protein per litre in milk. So we're going to say this is probably going to be normally distributed. And we want to test the claim that 1 litre contains 39 grams. So that's our null hypothesis. It's null, there's nothing wrong with it if you like. We're going to accept it. Okay. Well, we're going to start with saying that's the situation. That the null hypothesis is that the mean per litre is 39 grams, and the alternative hypothesis, HA, is that it's something different. Okay, it's not 39. We're going to try and see if we can tell whether it is consistent with 39. What, we're going to go out and do some sampling. Let's go and sample 10 cartons and find the mean and see if that's consistent with that null hypothesis. This is a very, very important idea, that the null hypothesis is something we start off with and we're going to test it along the way. Okay, hey, that doesn't seem too bad, does it? 38.4 from 39, that's only 0.6 grams in a litre. Is that okay? Sounds pretty good. Let's test it with some statistical theory now. So come down and let's have a look. Here we are. We're now told that we know the standard deviation of that grams per litre, and it's 0.8 grams. Okay, so the null hypothesis is that the actual, and here this is grams per litre, the actual grams per litre in each individual litre of this milk is, let's call it X, and it's going to be normally distributed around a mean of 39 and a standard deviation somewhere in here of 0.8, so here and here somewhere. So this will be 39.8, and take off 0.8, 38.2. So that would be one standard deviation either side. So well, it doesn't seem to be too far off, does it? 38.4 is in that bundle there. Hang on. That was an X bar. An X bar. Oh, that belongs on a different distribution. If we have taken the average of 10, watch it over here, then they should be close, shouldn't they? This doesn't look too bad, 38.4. If 38.4 was 1 litre measured. But actually, for 10 of them, should we be closer? Isn't that what the central limit theorem says? If you take 10, you zero in. Oh, well, let's have a look at the distribution we should be checking our x bar 10s against. This is x bar 10, the average of 10 in grams in a litre. Oh, it's narrower. Yeah, I remember. X bar will be distributed around the same mean, but with a smaller standard deviation. It's going to be this one here. And this is approximately, I already did on the calculator, mate, 2.253. So now let's look at it. And it's not looking so good now on this skinny distribution, because there's a mean of 39. One standard deviation in here, let's go out to 2. Two standard deviations would be 5. This would be out at 0.5 would be 39.5. And out the other way somewhere here, take off 0.5 will be 38.5. Uh-oh, now it's not looking so good. Okay, 38.4 is in this little bit here. And 95% of all the x bar 10s should be in there according to the null hypothesis. It looks like this null hypothesis might have to be rejected, doesn't it? Not much chance, because our x bar 10 is way out there in the wings. Okay, can we associate or assign possibly a probability to this? What is the probability if we have a mu equal to 39, which is our null hypothesis? What's the probability of getting an x bar on that distribution, 10, equal to 38.4? It's looking not so good now. Let's go down and do a z-score calculation. So what are we going to do a z-score? What is a z-score? Remember, you take the value on the distribution, take off mu, and divide by sigma. Except in our distribution, we're looking at the distribution of x bars, and the sigma, of course, is sigma on root n. So that's our z-score for the distribution of x bars. Okay, let's do it over here. That's what they've got. 38.4 minus 39 divided by standard deviation of the x bar distribution gives us this. Okay, now if we looked at the observed value of x bar and how it varies from the mean, if it's due to chance alone, it could have been 2.37 either way, to the left or right. Let's say it's chance variation. So what we're saying here is we are starting with a null hypothesis of mu equals 39, and we're working with that and assuming random variation due to chance on either side. So what's our chances? Let's have a look. This is a z curve now. We've made a z-score, so mu is 0, sigma is 1, so standard deviation is 1, somewhere at that point of inflection. Then it's out to 2, same thing on the other side approximately, neg 1, neg 2. Oh, it's down here somewhere. So as we said before, but what we're going to do is, because it's equally likely, but because you're suffering chance variation, give the people a go. So we'll say, well, we'll allow you to be that far either side. So we're going to find a probability of getting a deviation of z less than neg 2.37. We want to find that probability on a z curve, and then we'll give them a chance, we'll double it. We'll say, if it's really true that the mean is 39, and this variation that we're noticing is only due to chance, well, it could have been either side, so we will double it. Let's go down and do the calculation now. Okay, that one or that one, 2 wings, and therefore it's 2 times that one. Then you do it on the calculator. Remember, let's do this here. That'll be neg e 99 for the lower, somewhere way off to the left. And here, upper will be neg 2.37 and sigma 1 mu of 0 on the Casio. And it's that, 0.0178. It is very small. This is approximately 1.78% chance that if they are correct with their mean of 39 grams for the whole population, then we've only got a 1.78% chance of going in and grabbing 10 and then being that far away. Okay, so now it says, well, at what level do we want this to be significant? Well, we call the probability alpha at which to reject the null hypothesis called the significance level. The significance level used in this course is usually 5%. And so we would reject the null hypothesis under the 5% level of significance, or at the 5% level of significance, because there's only 1.78% chance that if that null hypothesis that we started with is going to be holding, and that is the real distribution on which we are working, then we should have had a bigger probability, 1.78%. Now, however, here we've got 1%, we would say, well, look, if you're going to look at it at the 1% level, we can't reject it, okay, because it's bigger than 1%. So at the 1% level, we wouldn't reject it. We'll come down later and talk to you about why we never say we accept a null hypothesis. You never say that. Let's go down and look at what's required now in this formal testing procedure. Because this can be a point of law in things like the Trade Measurement Act, there is a formal structure here. You must do it in a certain way. The steps are usually given to you in a test or an exam, but you should know of them pretty well anyway. Okay, the first thing is to state the null hypothesis, H0, and mu equals something. So here it's mu equals 39. Then we state what's the alternative hypothesis, that the mean isn't that. It's something else, higher or lower. And we're going to check it out. We select a significance level, usually 5% in this course. Okay, then we go out and grab a sample. We're going to check it out, mate. And here we checked out X bar 10. And it seems like a fairly small sample, but it doesn't matter in this one because we've said that the population is normally distributed. We reckon there are random variation going on there, and therefore it's going to be normally distributed. Okay, so we're saying here the parent population is normally distributed, and therefore our X bar 10s will be normally distributed with the same mean, but with a smaller sigma. Now, if we can't say the original population is normally distributed, central limit theorem to the rescue. Because the means will still be normally distributed, even if the original population isn't, if n is sufficiently large. So we can still get out of it. Our distribution of sample means would still be normally distributed under the central limit theorem as long as n was sufficiently large. Okay, now this is called the null distribution. The distribution of sample means is going to be normal with that. So this is called the null distribution, distribution of X bar. Please be careful here. And here it is, 39, and that's our value that I mentioned to you before. Okay, please be careful. Sometimes they ask for the null distribution of the test statistic. Oh, now that's a bit of a trap. Of the test statistic. And if you're doing that, that means what's the test statistic? Z. And Z is normally distributed with a mean of 0, standard deviation of 1. So it's 1 squared there. So watch out for that. Have they asked for the null distribution of the sample means? They might not say the sample means. Or have they asked for the null distribution of the test statistic, or the distribution of the test statistic, which of course is the Z test. It's Z distribution. Okay, the null distribution is critical. It allows us to calculate the probability of the observed or more extreme events happening if the null hypothesis is true. I would like to put it differently from that. I would like to say we work with H0 and check whether our X bar of whatever we do, X bar n, could have come from that distribution. From that distribution. That's what we're doing here. We're saying we have a null hypothesis, we'll work with that, we'll create a distribution of the actual volumes or weights here. Then we'll go out and test it with a mean, and we will construct a distribution of sample means based on the original distribution. And if that doesn't give us a reasonable probability, we're going to reject that original distribution. Okay, so coming down here, the last steps, what we did back there, use the sample mean to find the test statistic, x bar minus mu on that, and we found that before, and that's why it's called the z-test. Sometimes called the z-test on a calculator, and we'll do that in a minute. We now want to find the probability value, a p-value. So either tail, we're going to give them two chances. So normally we just double one of them, only look down one end by symmetry. Remember, of course, all the normal distributions are symmetrical. You know why. Random variation, equal opportunity, be on the right or the left side of the modal valued, blah, 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 blah. Remember that? Okay. Now, we're going to have to reject or not reject. Now, at the 5% level, the p-value is less than the significance level. Then if the p-value is less than 5%, we reject the null hypothesis at the 5% level. You had to have greater than 5% chance of this happening. If p, here if it was 1% level and p is greater than 1%, we do not reject the null hypothesis. We say there is insufficient evidence to reject. We can't say we accept. Never, never, never say you accept it, because we have not shown. We have not shown any value. Not shown mu is 39. So if we say we accept something, it means we're accepting that number 39. Well, hang on. All we can do in this statistical theory now is to say, is it within the realms of chance variation that 39 could be true? And if the probability is high enough, yeah, we say it's within the realms, but we haven't actually shown. So you can never accept a null hypothesis there for a mean of a stated value. You can only say, we do not reject it. You're in the ball game still, mate. Okay, that's the idea. Well, let's come down and have a look and see what we've got here. You might be saying, hey, I like those calculators. A bit crowded window though, mate. But I like those calculators because it means I can do something with the means on the calculator. That's meaningful. This is all about means, mate. Anyway, mathematics coaching school knows that the results of their final test are normally distributed to mean 74%, standard deviation of 7%. A new coaching technique, which is cheaper, we'll go for that, is reported to have the same results, but they're going to trial it. They trialled 40 students and they found, the mean went down a bit, standard deviation of 6%. Is there sufficient evidence to say that this is not a cheaper method but not as good a method? There's been a drop of 2% on that sample of 40. Now, most people in the street, and you're not one of them because you're a budding young mathematician, would say, that's a 2% drop, give it away, mate. Oh no, hang on. We took a sample of 40. Is 72 on that mean of 40 within the realms of possibility of just being random or chance variation? Let's do the analysis. So here we are. Mean of 74 for our null hypothesis, not 74, 5%. Sample mean, so distribution, null distribution is 74, 7 on root 10, remember there's sigma on root n, where n is 40 here. This is the standard deviation of the distribution of x bars. Okay, so now notice that we use the 7 in here. Right, that's from up here. That's part of the null hypothesis, part of the proposed population. We don't use the standard deviation from the sample. All right? Don't do that. Now, we might have to use that if we didn't have a population standard deviation. But that is what we're testing, the population. So if they have a mean and a standard deviation, we don't introduce any more errors from our sampling and put our standard deviation for our sample of 6% in there. All right? It's all testing a null hypothesis about the population, not about our sample. We're going to see if our sample fits on that null hypothesis. Okay, so let's have a look at that. And so if we do that, we get this score here. All right, neg 1.81. What's the probability of being less than negative 1.81 or greater than the value on the other side? Double it and get that probability. Okay, so using their NCD on a Z distribution. Alright, so because it's greater than 5%, there's insufficient evidence to reject the null hypothesis. And we therefore say it's quite likely that they have the same result. We have not shown that this cheaper method produces a lower result. Let's now look at technology here. Okay, let's just go back there a bit close to the top there. So here with our technology we're going to come in to stat mode, and then of course we want to hit F5 in here, and then here it is the Z score here, and what we're going to do, oops, hang on, I've just made a mistake there, we're not hitting F5, we're hitting test here, F3, testing F3 gives us a Z test. If we hit F1 then we get this window, and we want one a sample here, one sample only, 1S, F1 test, one sample Z test. This comes up, you must have variable data, and here it is mu, make sure you have mu is not equal to mu naught. Sorry, mu is not, we've got this symbol in here, is not equal to. That's what we're testing, just a deviation away from that. And the mean, the standard deviation, and then X bar that we've got, and the sample size, we're putting those in. So here therefore we've got our mean is 74, it should be 7, X bar 72 and 40. So that's what we have to put in over there into that window. We have to enter the values that we have found, and then if we push execute, what have we got? Down here, got our statement, and there's our deviation, and there's the probability. So this is a good way of getting a Z score for a distribution here of X bars, isn't it? Because we can actually go through that and that Z score will be produced. So that's an interesting way of getting a Z score, if you like. Alright, so it comes to the same answer, of course, here, and 0.0708 over here. So you can check your work using that. Okay, so what we're doing is looking at the deviation of our X bar away from our mean under the null hypothesis and change it to a Z score. Okay, let's go down and do some. Here's 7H1 from Hayes, and Harris. So you might go through and do the whole box and dice here with the Z test and see what you think. I'll just show you, pause it now and have a go. I'll show you the solutions. Question 1 and question 2. Let's go on and do something else. Some variations here, some interesting variations. Remember what we're trying to do. We're trying to check this out. Okay, we're trying to check out what is really happening here with these claims that people make. Here's another claim. The mean volume of bottle is 503 ml. Testers claimed 10 bottles were selected. Measurements were those. And the claim to be made that 5% is known that the population standard deviation is 1.8. So we're doing it at the 5% level. And what we're going to do here is we're going to assume it's normally distributed. There's the stated mean, and that's the null hypothesis. Alternative is it's not that. We're saying there's random fluctuations, so we're going to assume X is normally distributed, so the mean will be normally distributed with the mean of the population that they have stated, claimed, and with that sigma. So there it is. There's our X bar, fairly close to it. The Z score now, x minus mu over the sigma of the distribution, and the sigma for x bar distribution is sigma from the population divided by root n. Remember that from before. So we got neg 1.722, and we double that to be less or greater than on either side of the mean of naught, and we get this. So there is insufficient evidence to reject the claim. Okay, 502 sounded a little bit small, but at the 5% level here, under the null hypothesis, there's still an 8.5% chance of that being correct. In other words, it's a bit disappointing, but as young statisticians, you know that by chance this could happen. Chance variation. You've got to have more evidence than that. Okay, because remember, with this inferential statistics, we're taking samples from a population. You can never tip out all the bottles and work out how much is in there, because there'll be nothing to sell. So that's our dilemma. Okay, it's making an inference, and we've got chance variation here all the time. Random factors will affect the bottling process. Okay, come down and have a go. Right, there we are. What you need to do is the same sort of process. Go through this formal test. Okay, have a go. And let's have a look at the answers now. Formal test, question 3. Make sure you've stated it like that. And particularly the final statement, you either reject or do not reject. You never accept a null hypothesis because you actually haven't proven any values at all. And there's question 4. Let's go on and see what else we can do. Hypothesis testing when the population is not necessarily normally distributed. Okay, we know that if it was, then x bar would be also. This may not be true if x is not normally distributed. But the central limit theorem says that x bar is approximately normally distributed with mean that and standard deviation that if you have sufficiently large n. I want to write this here. Sufficiently large n. And then it's approximately normally distributed. Okay. And here's a diagram from before. And we're saying, well, there's a wacko non-normal distribution. But when we take means from it, various sample means here, they are going to suffer random variation. They're going to produce approximately normal distribution with the mean of the means there centered around the mean and a sigma of the original population, sigma up here, divided by root n. So away we go again. We can still test that whether this null hypothesis is going to be rejected or not by accepting the mean and the standard deviation and then testing whether our distribution of sample means based on that is going to give us a reasonable probability of getting such a sample. That's what we're doing. All right, let's come down and do a few now. Here's one. Susan's resting pulse rate has been 55 beats a minute for many years. Standard deviation of that. She checks it at pulse rate 8 times a day and finds there's a mean of 56.2. Is that significant? Has it gone up? Has it changed? Null hypothesis is no, it hasn't. 55. Alternative hypothesis is not 55 anymore. Significance level 5%. How many times did she measure it? 40. Sample mean was 56.2. Population standard deviation is 2.6. Now, we don't know whether the random variable x is distributed normally, but n is pretty large here. It's 40, so we're going to say the central limit theorem will apply, and so the distribution of means is going to be approximately normally distributed. Mean of 55, standard deviation, don't forget, it's of means, 2.6 over root 40. Okay. And you could do it by hand or put it into the calculator, check that, and you get a p-value of 0.001. 0.00351. You really should put in here the Z value is x bar minus mu over sigma on root n, and work that out. I think that should be in there, the Z statistic, and then the probability. And because it's less than 0.05, then you're going to reject the null hypothesis, and it looks like her pulse rate has changed. And you may say, if it's been rejected, which direction it went in. It's gone up. So the deviation here is 56.2, and that's a significant deviation in the upwards direction. All right, come and have a go. Have a look at these now, question 1 and 2. We can pause the presentation, and we'll come back and look at the solutions in a minute. 3 and 4. Okay, let's have a look at the solutions. 1 and 2. We'll just go up a bit more, see if we can get a bit more of 2 in there. And that's the rest of 2. And 3 and 4. Okay. I like their comments here about insufficient evidence to reject null hypothesis. Okay, that's very good. All right, come on down, a little bit more to do. And this is an important idea for later on. Rejection region for the null hypothesis. What are we doing? We're working out a Z-score. So when is a Z-score too far one way or another? Well, if you look at 2 standard deviations either side of the mean is what we said before, wasn't it? To have 95%. But it wasn't quite correct. There's 1 standard deviation, 68%. 2 was supposed to give us 95%. It actually is a bit less than that. If you put it on the calculator and put your lower neg 1.96 upper 1.96 on a standard normal curve, you'll find that's closer to 95%. So here it's actually 1.96 sigma above the mean and 1.96 sigma below to get that area in there more accurately at 95%. Okay, so in our calculation work, not if we're just talking about roughly slicing up the distribution, but if we're talking about our calculation work, the rejection region for the null hypothesis in either side is that value below which in total there's 5%. So that means 95% in the middle here. So that is actually 1.96 sigma on the standard normal curve where mu is 0 and sigma is 1, of course. That is 1.96 sigmas, which is just the number 1.96. Okay, so you could actually, when you see the Z-score straight away, if you knew that it was less than neg 1.96 or greater than 1.96, you could immediately know you would reject it at the 5% level. But really, don't forget, it's a formal test. So you really should go through each of the steps as an argument for rejecting or not rejecting the null hypothesis. Let's come down now and have a look at a problem. A liquor chain claims that the mean price of wine has not changed from what it was 12 months ago. The mean price was $13.45 for a 750ml bottle. Random sample of prices of 389, that's a good sample size there, has a mean price of $13.30, standard deviation is 25 cents. Is there sufficient evidence at a 5% level to reject the claim? So the wine has not changed. Well, it looks like it's actually gone down, hasn't it? $13.45 down to $13.30. Let's check it out. There's the null hypothesis. Alternative is it's not $13.45. Now, we don't know the standard deviation, so we will use the sample standard deviation. And also, that's not too bad because n is large. So if you take a large sample, you're going to get a better estimate of both the mean and the standard deviation. So we are resorting to S is approximately equal to sigma. For n large, we would prefer sigma. A statement about the standard deviation of the population, we don't have that though. Let's look at the test statistic. 1330, take 1345 over that is negative 11.8. So since z is less than 1.96, we reject the null hypothesis. There's no difference. The price has changed. It is looking like it is lower. It looks like there has been a move down from 1345 to 1330. Okay, let's have a go at some problems. 7H3, question 1 and 2. Just pause the presentation and have a go. And now let's have a look at the answers. Okay, 7H3, 1 and 2. Try and set it out down the page a bit more than that. Alright, the last little bit now is to test the hypothesis. Null hypothesis mu is 40, mu is not 40, a random sample of 60, that's good size. And to have a mean x bar and a standard deviation S, so that's the sample standard deviation. For what values of x bar will the null hypothesis be rejected at the 5% level? In other words, when you go out there and get a mean, can you straight away say how far that mean should be away from 40? Well, let's go straight to the Z statistic. We don't know a mean, and the general rule is if you don't know a mean, use the Z statistic. So Z statistic is what must x bar be away from 40 divided by this, there it is. And what's the rejection region if it's less than neg 1.96 or greater than 1.96? Because between those two you've got 95% of all the scores there. So down to neg 1.96, because this is mu is 0, a sigma of 1, and up to 1.96, that's 95% in there. Got to be in there if at the 5% level we'll accept it. Okay, so let's work it out. X bar minus 40 can be less than or equal to neg 1.96, it'll be rejected, or greater than or equal to 1.96. So multiplying that across there, adding 40 and these two values, so it says x bar must be less than or equal to 38.2 or greater than or equal to 41.8. So by doing this, you're preempting, if you like, the Z test. Because when you get your mean, straight away you'll say, oh, it's too low or it's too high, we can reject the null hypothesis. Okay, so it's just a little trick there to think about having an x bar in mind at the edge of the rejection region there. Alright, want to have a go at a couple like that. Let's have a look there. 3 and 4, and I think we're going to finish up then. I'll show you the answers. And here we have it here. Our last two answers there for a manipulation of the Z test. Keeping in mind now that if you have a missing mean or a sigma, you will best attack the problem with a Z score. And Z scores are fundamental to this area of inferential statistics. Well, I hope you're happy with building up your skills. You better go back and have some of that milk, mate, because it's thirsty work. We have one last section in this inferential statistics course in talking about trying to find out what that mean really is. What is it really? We're checking out what it might not be here in this presentation, hypothesis testing, but what is it really? How can we find it out? Something to think about. Anyway, cheers for now.